All right, hello, and welcome back to Minecraft Agoraphobia. Cheers, Kevin here, and I'm just recording a quick intro from the future because the video that you're about to see actually was recorded at the tail end of yesterday's video. So if you haven't watched yesterday's video, it's probably worth going ahead and peeping at that one first because, yeah, we're going to get into some very disgustingly nerdy stuff today. We're going to live pretty much entirely in Terminal Land, so get prepared for that. And, yeah, that's all I really have to say. I will let past myself take it away, and I will see you in the next video. So I'm actually going to set aside task 3 for this episode because I had an even cooler idea. So we had that example after we got our yield where we said something like, I don't know, what was it? Forward yield, forward yield, blah, I can't talk. And then we gave it a function and said, you know, robot dot swing down to break a block and then end. It was occurring to me as I was writing that and writing some other stuff that what I really ought to be able to do is something like 3 and then in parentheses fy as my string. And then I could have the same function, right? Because I could group those things and that would be the same thing. So could we update our program to do that? Well, the short answer is no. We can't. The reason for that is that balanced parentheses are something that actually you cannot solve with regular expressions, and by extension, almost certainly can't solve with Lua stuff either. Now, if I'm wrong on that, I'm pretty darn sure, but please let me know. Lua does have a mechanism for finding balanced parentheses, but it doesn't grab the stuff in the middle of them, so I don't think that's something we can really make work. The challenge is that if you're trying to pattern match stuff, you could do something like, hey, 2 times I would like to go forward, and then 5 times yield and go up, and et cetera, 45 down, and yeah, close all those parentheses there. And figuring this mess out is a nightmare. What we are actually doing is we are defining a programming language. A very simple one, but a programming language all the same. And so what we have to do to make this work is to write a parser and eventually an interpreter. So just to be clear, this is massively over-engineering stuff. So if that's the sort of thing that triggers you, then this is a good time to click away from the video and I will see you next time. But for those of you who really want to nerd out, let's go ahead and dive into this. So I'm going to write out some Bnf notation, which is how we define languages, which is confusing and weird. I'm going to say, okay, our program is an expression. And an expression is a pair, or it is a pair and another expression. Okay, so we're just defining at a high level what this movement language is. So what is a pair? A pair is a term, or it is a number and a term. Okay, what is a term? A term is either a directive, I don't know, yeah, a directive, or it is the literal quote, the literal open parenthesis, and then a new expression, and then a closed parenthesis. So this defines the language that we're working with. I suppose we could also go up here and just say that this number is lowercase because it's not really a high-end thing. We could also say that a directive has to very explicitly be a single character. If we want to be pedantic about it, which who knows, maybe we do. Okay, so before we get into actually writing the parser steps, I want to write a small utility function. Let's go ahead and pretend that we have a parse, let's see, a parse string. And we'll come up with some example. Let's say 2, 3 AB, down, up, forward. Okay, there is our parse string. If we try and expand this out ourselves, we'll get AB, AB, AB. That's 3 times, and du. And then so 2 of those, join those together, and then an F. This is what our result should look like. Okay. Now, of course, I'm using A and B. I'm using random letters because we don't particularly care now. We'll integrate this back in later. We'll say solution is that. Local solution is that. Parse string, I guess we can say local parse string is that. Okay. So somehow we do want to make sure that what we get out is the same as our solution, or unless I did something wrong, which is entirely possible. What I would like to do real quick is to write a function called chomp, and chomp is going to take a Lua pattern. What it's going to do is it's going to try and pull this off of the beginning of the current parse string. Because the way that we have to process this is we really have to go kind of character by character for the most part and say, hey, I'm going to look for a number now, so go ahead and grab that number and then take it off the top of the string so that when we go ahead and continue parsing the rest of the thing, it's not there in the way. So what chomp is going to do is it's going to say match is string.match parse string, and then the pattern. And that function just takes 2 arguments. So this is going to look through the string and take a pattern. The only thing that I want to modify real quick is that I want to say the caret character. And this means that we want to only look at the very start of the string for a match. If I'm saying, hey, all right, I'm ready to pull a number now. Well, it doesn't do me any good that this number is here because that's not the number that we happen to be looking for right now. So I'm going to say, hey, try and find a number. I can call chomp and say, hey, I'd like to grab some numbers now, please. It'll say, okay, I will go through the beginning of this string and try and find that number and assign it to this variable match, and then return match. But before we return match, we're now going to trim the string. So we're going to say parse string equals string.sub, and this is the substring. And we'll say string.length of the match to -1. Actually, you know what we could do instead, because match may not exist. What we could do as well is just say string.gsub and parse string. This is probably a little bit slower, but that's okay. Pattern. So we just did this pattern lookup to find the match. Now we're going to say, hey, if you find that pattern, go ahead and replace it with an empty string. So that effectively does the same thing and keeps the whole thing in place. All right, let's go ahead and test this real quick. I'm going to say rar str equals rar, and then let's say print str will print chomp of it's dealing explicitly with parse string. So let's test parse string. Let's look for 2 and then an open parentheses. We'll say I want to chomp those 2 things off, and parse string. Actually, you know what I kind of want to? Well, no, that'll end up being a string that's too long. I kind of want to make it multi-digit just so we can test it, but that's fine. The other thing I have to do is because this is a pattern, I need to use this to escape this open parenthesis. Let's go ahead and run that. Okay, so this is the string initially. It says, hey, cool, I got your match. Here's your match. And then here is what the string is after it's gone ahead and gotten our match. This is going to make things a lot easier for us. Okay, now what we're going to do at the very bottom here is I'm going to say parse, 2, 3, AB, DU, F. All right, so we'll go ahead and say this is going to be the program, our test code. I'm going to go ahead and make the parse string empty now. And I'll go ahead and put the solution down here. Let's go ahead and just print it out directly, because then we can go ahead and validate that at some point. Okay, so if we run this, it's going to do nothing. Whoops, try to call a global value. All right, okay, so it's saying, hey, parse doesn't exist, so let's do that. Let's write parse. Parse is going to take a string, and it's going to say parse string equals string. And then it's going to say parse expression. If we look at the way that our definitions work, we say this is the top level of our program. A program is an expression, and an expression can be a pair, which is a number and a term, or it can be an expression and a pair and another expression. So we need to write something that will parse that. So we'll say, okay, cool, parse the expression. And we're just relying on this parse string global to kind of exist and be the thing that we're looking at. So we're going to call this function called Parse Expression and say, hey, go look at the parse string and see if you can get an expression out of it. So let's go ahead and write Parse Expression. And Parse Expression needs to get a pair. So we'll say local pair, regardless of what... regardless of which path it goes down, it's going to be getting a pair. So we'll say parse pair. We'll say the local pair is the parse pair. And then we have to figure out exactly which version of the expression, which rule we're going to resolve by. Are we going to be a single pair, or are we going to be a pair and another expression? And that's an open question. I think instead of calling this pair, I'm going to call this left, because if we think about the way that this will eventually structure, it'll be sort of a tree. If we have, so for example, if we were to try and draw this ASCII-wise, this would become something like, we have an expression that has a 2, and then another expression, which breaks down into a 3, and another expression, which breaks down into an A, and another expression, which is just a B, and et cetera, et cetera. It becomes this bit of a hornet's nest. But the left side, so the left side of what our expression is going to be that pair. In either case, we just may not have a right side on that tree. Okay. So we have this, and the way that we know whether we're going to be just a pair is that, hey, there's nothing left in the parse string. If there's nothing left in the parse string, well, then we can't have another expression after it. Also, I'm going to say that if we are let's imagine that we're somehow going through some nested stuff, and we're trying to evaluate an expression inside these parentheses. Well, we know that if the next character is a closed parenthesis, then yeah, we're done parsing this expression too, because we can't extend outside of the closing parenthesis. So we'll say if string.len of parse string equals 0, or string sub, so I'm going to get a substring, because you can't, unlike some languages, you can't just say, hey, I want to get the first character or whatever like that. So substring 0, 1 is equal to this closing parenthesis. Then we know that we're just going to be the left side. And in fact, because we're just going to be the left side, we can just return that left side. So we'll go ahead and return left. And otherwise, what we're going to do is return a node, a graph node for our parse tree. Let's go ahead and create that. We'll give it a type. We'll call it an expression. I'm writing in the wrong language. Equals expression. And we'll say left is equal to this left. And then the right is going to be equal to, well, if we're going down this path of resolving our language, the right is going to be an expression. So let's go ahead and just parse an expression. We'll say, hey, the rest of the string is there for you to find. Go ahead and parse it. And whatever gets returned from there, that's going to be what's on the right side of our graph. Okay. I know this is confusing, but it's awesome. So we're doing it anyway. Okay, so that implies we have a parse pair. And a parse pair is going to have possibly a number. And I think maybe I should have ordered these. Yeah, I think I probably should have ordered these in the. I don't know that it necessarily matters up here. We'll go ahead and say we'll assume that it does for some reason. Let's go ahead and say local n is going to equal, and here's where we're going to try and actually chomp some stuff off of the string. We'll say chomp. So you notice, yeah, the expression didn't actually strip anything out of the string because it's entirely made up of these lower components. But the parse pair is made up of a number, potentially at least. So we've got to try and match for it. So we'll say chomp, and we'll say a digit, one or more digits. And then we can say, if we got the n, then great. Actually, you know what we can also do is we can just say local term is a parse term. If I pop this back up, let's go sideways. That's not particularly clear either. If we pop up, yeah. So in either branch case, we're going to look at now the rest of the string to find the term. The term, if we're looking at this, if we have a movement pattern of 2A, then A is the term in that scenario. So we could have 2A or we could just have A, and in either case, there's a term there, so we've got to parse it. Okay, so we'll grab the term. We'll say if n exists, then we're going to create another node, and we'll call this a pair, and we'll say the number is going to equal, and there's a function called toNumber, which will take the string and convert it to a number, toNumber n, and the term is going to equal the term, which we've already parsed in theory up here. We haven't written that yet, but that's okay. Otherwise, we need a then here. Yeah, otherwise, well, then we resolve to just a term, so there's no reason to have a pair here because it's just kind of an in-the-way node, so we can just return the term itself. So the expression may resolve to just a term, despite the fact that we say an expression is a pair is a term is blah, a directive is a character, blah, 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 blah. Okay. Function, parse term. And now we have to decide whether or not we're dealing with parentheses or not. And that's honestly pretty darn easy. So let's say if chomp that, and we actually have to escape that because it's a special character in Lua patterns. If we have that, then we know we've got to figure out we have an expression. Otherwise, and we have an expression that starts now with the beginning of the remaining string because we've just chomped off that opening parenthesis. Otherwise, we don't have an expression, and what we do have is a single character, which is up or down or left or right or yield or whatever. So let's go ahead and return. Oh, you know what? Actually, I need to, up here, also return that type. You got to make sure to be explicit in Lua. We'll say type equals directive, and value equals, and we're just going to say chomp any character. I don't care what character you get, but the next character is that directive. It's the U, or it's the left or the right or the up or down or whatever character we may be pulling in. If we have an expression, well, then we need to parse an expression. Actually, no, we can't just return it. We need to save it first. We'll say XPR equals parse expression. And then we also need to get rid of that closing parenthesis. So we'll say chomp that closing parenthesis, and then we can return the expression. I can type. Okay. Believe it or not, I think this is actually all that we have to write. Well, I mean, almost. Okay, so of course it doesn't print anything. Parsing itself, parsing on its own doesn't do any printing. And unfortunately, because Lua is Lua and doesn't have fancy stuff, it doesn't print out. Actually, why doesn't it print out anything? It should print out something at least. Oh, right. We need to actually return the parse expression here. If we do that, it says, hey, cool, I made you a table. And of course, this is a nested table of tables and of tables of tables of tables. As it turns out, the first thing that we're going to get back is an expression, one of these up here. So it's going to have a left and a right. And if we wanted to, we could go ahead and print that left, and we could print that right. And those are all tables. They're different tables. They're all tables. Not particularly helpful. What we need to do last of all, we have this tree that we've parsed this thing into. We've parsed the code. Well, we've lexed the code. Well, now we need to write a visitor that's going to start at the very top of the tree, which is that first expression that has a left and a right branch to it. And it needs to walk down the tree and execute whatever it's supposed to do. So we're going to create a function called visit, and we're going to tell it, hey, visit a node. And this is what we're supposed to do whenever we visit a node. So we'll say if the node type is equal to a directive. For now, there we go. Then for now, all that I want to do is I want to print the value of that directive. So I don't care what thing we got out of it. I just want to print that out. We're not worrying about actually executing the robot stuff. This will eventually be do the robot stuff. This will be the place where we actually execute anything, because everything else is just number multiplication and blah blah blah. Instead of print, I want to use io dot. Is it io dot print? Okay, it is io.write, and the reason for that is that it doesn't add new lines after everything, and I want this. I want all these characters to be written out on one line so we can compare it with our solution. Okay. Else if there are two other types of results that we can end up with. We can end up with a pair, or we can end up with an expression that has a left and a right side. So if the type is a pair, well, the only case in which we actually have a pair is when there's a number, and I suppose it could be 1. But when that's the case, we need to just execute the term that number of times, right? We have 2a, then we just need to run a twice. We need to visit the a node twice. And even if the term isn't itself an expression, we need to visit that entire thing 2 times. So we can just do that. We can say for I equals 1, comma, node dot num do, and we'll just say visit. So we're recursing here, visit node dot term. So 2 times, go ahead and visit whatever. Then the last case, which we can just assume is an expression, we can just say visit node dot left. So visit first the left-hand side of the expression, because if we're breaking this up, the way that this expression works is you get something like this. Actually, no, that's, you get something like this actually, because this itself is one expression. But then inside here, you have this, and then you have this. Yeah, okay, anyway. Visit node.left, and then visit node.right. Okay, I think this should work. Let's see what happens. Oh, okay. I need to print visit. Oops. So actually, we don't need to print visit. Yeah, we don't need to print anything. We just need to visit that parse tree, and it should actually do the writing right there. If these match up, then we have written a lexer, parser, and interpreter for this little bitty movement language. Okay, that's not helpful. All right. So that's fantastic. Either I managed to manually come up with the wrong solution and code the wrong solution without really coordinating with myself on that, or, we just wrote a programming language. So that's pretty neat. And the last thing to do is just reintegrate this with our move program. So if we look at, basically all we're replacing is this here. Okay, so granted, that's we're replacing, we're putting a lot of code in that place, but that's okay. Let's grab these, plop those in here. Indent those. Yeah, so we're in here. We can remove this. Say local parse string. We have a function chomp inside here, which needs to be inside here. Everything else needs to be inside here as well. Actually, I shouldn't have deleted that yet. Perform dir. So instead of we'll take this perform dir. So instead of having this perform dir in this kind of relatively naive loop here, we can go ahead and jump into our visitor, and where we have our do the robot stuff, we'll take out io.write, because I don't even know if that exists in Open Computers. We can just say now perform, and what was I saying? I should put that back. Perform no.value and call it. So this in theory should work. We'll have to jump into KOS. KOS, what? Okay, it's getting late. We'll have to jump back into the game and see if it does. Okay, so as I said, the whole reason I wanted to be able to do this was to not have to say things like forward, yield forward. Yeah, let's do it that way. That'll make things easier. Let's just do 3 yield forwards and see if that works. We do need to pass it then the function of what to do on yield, which I'll say robot.swing down and end, and save that. And are we ready? Let's do a move test using our brand new language. Oh, you know what? We're actually, yeah, I take that back. We never actually initiate the visit. We need to actually do that. Okay. Where exactly does that have to go? Oh man, we have all this stuff that's got to be nested in here so that this parse string is in scope. Okay, yeah, I guess at the very bottom of this inner block, it actually has to parse the string. I think we get it as path. So we'll say visit parse path, and I think that's right. We go up. Yeah, path is in here, and then f is the function. But that's, yeah, we don't have to worry about that. All right, move test. Let's do it. Ha ha! Okay, there we go. Ladies and gentlemen, we have written a programming language and for all of mankind, the greatest moving language, and an interpreter and parser, to boot, all in a day's work. So that is definitely going to do it for me today. Let me know what you think. Let me know. I know it can be perplexing, but I'm very excited, as I'm sure you can tell, and I will see you in the next video. Cheers.